All right, over the next half hour, I just want to give you a brief glimpse of what's going to happen in CUDA 6. We can come back to the optimization part later on, but given that we have some people who were otherwise not joining the optimization talk, let's just go through this one here quickly. As I mentioned before, CUDA 6 is about to come out. People who are registered developers can download it within the next few weeks. Some people already have it, so we currently push out the release to a small group of developers. We collect their feedback. We build the release candidate, ship it out to a broader audience of registered developers, and then the actual release happens. I'm terrible at memorizing dates, and so I couldn't give you exact numbers when this will happen, but it's going to be first quarter of 2014 for the actual release. So, but just to give you a feeling of what's going to happen, there's basically 4 groups of different improvements that happen in CUDA 6. The biggest one and the most exciting one is unified memory. There's a first glimpse of UVM coming out with CUDA 6. But it's not the only one change that we have. There's also an improved version of the BLAST libraries and the FFT libraries. There's going to be an improvement on the GPU Direct RDMA. That's something that most likely you will not need to touch yourself. That's more geared towards middleware developers. But it's something to know that these things happen. And but what is more important is there's going to be some cool changes in the developer tools. Oops. All right. So what is UVM about? We spent a lot of time yesterday and also on the OpenACC side to talk about managing these separate address spaces that we have on the host side and on the GPU side, right? And it's all about the question of how do I efficiently transfer data between my host memory and my GPU memory. With UVM, we pretend that this PCIe Express bus does not exist. So it's a mechanism that helps you hide the PCIe Express bus and allows you to access data from the GPU that actually sits on the host side and vice versa. So as you can imagine, it's no silver bullet. I mean, we still have to move data across the PCIe Express bus. That's mechanics that's there. So it's, at least in the first iteration, it's not meant to be a performance feature. It's a convenience feature. Let's look at the how this helps. Right? When you look at something like a piece of code that sorts a file, we start out, we have to allocate data, we have to read the data, we sort the data, we use it, and we do some cleanup. With UVM, actually don't have a, well, with UVM, what you will have to do is we have a new function for mallocing data. And now this is not just CUDA malloc where you're allocating data on the GPU, but we are having something called CUDA malloc managed. And you don't need to worry where this data is going to be. It's just, we're saying this is data that possibly can be moved between host and GPU. And then we can use it. So there's no explicit data transfers between host and GPU. All we're doing is we're using this data. So when we're reading the data on the host side, because this file, that's stuff that's in the file system, so most likely data will stay on the host side. But then when we call the sorting routine, our pages that contain this data will be moved to the GPU. But that's all transparent to you as a user. So it just tremendously simplifies the initial port of the application to GPUs. And that's probably the biggest bullet point here, is that you have just the one single pointer, right? Yesterday, remember the example that we had about even the very first one that you wrote kind of by just saying, OK, move now this data to the GPU and pull it back. You had 2 pointers for basically pointing at the same data. You had the host pointer and the device pointer, and you need to keep track. I told you prefix it with a D underscore or whatnot to keep track visually of it. It's kind of clumsy. It definitely gives you optimal control. I mean, at that point, at that level, you know exactly where your data is. But maybe you don't care about that, at least not in the first iteration. So it's all about simplifying porting. And then the other thing is that it also has the benefit, it eventually will give you better performance because you're migrating data to the memory space where you're actually needing the data. Again, as a programmer, you ultimately have more insight about who will need the data at what point in time and for how long. So you will still be able to outperform that with a finely tuned, handcrafted implementation. But in some cases, it can be actually fairly tricky. And we come to a few of those in a second. And the good thing is, so even with unified memory, you can do hand tuning. You still can do explicit data transfers between host and GPU. It's just no longer necessary. So basically what it says is that what previously was necessary to do, explicitly staging the memory between the different memory spaces, becomes a tuning or an optimization step. Now, one case where it just tremendously simplifies your life when you have C++ applications. And I mean, that's one of the targets for unified memory is C++ applications where you have fairly complex objects, complex data structures that need to be moved between host and GPU. Imagine just the following case where you have a struct that has whatever, 2 properties, integers, and a pointer to a string, or just a string, basically. So in CPU memory, it looks like this. Now, if you want to transfer this, you actually need to make 2 copies. You first have to copy the data structure itself, and then you have to copy the string that's pointed to with this pointer. If you would ignore this guy here, the second copy, well, you would end up with a pointer as the third entry that still points to this address on the CPU, to this location on the CPU side. Now, when you look at this, how you write it currently in CUDA is you have to malloc both space for the struct and you have to malloc space for the actual text. Then you have to do these copies, right? And then you have to make sure that the pointer that you're inserting there is actually the one that points to this location rather than the pointer that goes over there. So it's, as you can see, fairly clumsy. A lot of extra work. With unified memory, it all collapses into basically just using the data. And you leave it up to the runtime, to the operating system, to figure out, or to the driver, to figure out when to move this data and where it should be placed. This can be particularly interesting when you have things like data structure like linked lists. Right? Copying a linked list over and fixing all the pointers and stuff like that. That's why it's easier when you just have large arrays and you move them and you have no sophisticated data structures. But people want to do those kind of things. And yeah, at the moment, it's just a lot of work. And with UVM, you're placing your data, you're creating your data structure in this form. Given that the pointer, I mean, we have that already now, but given that a pointer can identify just by the pointer itself, whether it's pointing to memory on the host side or the GPU side, you also will not need to have to fix the pointers that you're using in your linked list once you're moving it to the GPU. It's all going to be totally transparent to you. So from the CPU side, it looks like a regular access. When you're accessing from the GPU side, it looks like a regular memory access. Now, I should probably start selling vacuum cleaners or something like that. And obviously, there's some flip sides to this. The biggest danger, as you can imagine, is that you're sloshing data back and forth between host and GPU. So you will still, at least at the beginning, you need to keep in mind that we have the PCIe Express bus underneath, and it's still expensive to move these pages between host and GPU. But the good thing is, it becomes just an additional consideration. It becomes an optimization step, and it's no longer necessary to start with. And yeah, as I said, the main target for this is C++ applications. Yes? Yes. Yeah, and so actually I have a slide. Let's see. Oh, here is the unified memory roadmap. So right now, CUDA 6 it's really just exposing this mechanism. It's for people to get used to it, to play with it. But we have to live with the fact that we're not actually having a mechanism on the GPU that gives us the page faults. So just when Kepler was designed, that was not one of the requirements. So we have to jump through some hoops to mimic the behavior of migrating pages. That's also why we cannot just use the standard system malloc and then totally under the hood move data back and forth, but we have to have this CUDA malloc managed call at the moment. Let's see. Yes, so it's basically something that just gets us going. So this is with CUDA 6. Then CUDA 6.5, or subsequent versions coming out later this following year, there will be more optimizations. One of them is being the question of like prefetching of pages, question of what is the optimal size and so on, allowing the programmer to help a bit with where the data should be moved. So those are optimization steps that are coming up in the next release. And then once the next generation GPUs comes out, the ones that have true mechanism for detecting page faults on the GPU side as well, at that point, it will no longer be necessary to have the CUDA malloc managed. Then we can just use the system mallocation. And yeah, at that point, we will have true unified memory between host and GPU. Yes? Well, first of all, we're at that side. Yeah, I think that's a fairly open secret. That yes, ARM is one of the possibilities of having some more latency optimized compute capability on the GPU side. It's still the question there remains of how do you link your throughput optimized processor and your latency optimized processor together. Right? At the moment, we're doing that, but the link between the two is going to be the PCI Express bus. I mean, that's what we currently have. In the future, who knows what we have in between. But key is that by changing this programming model, by no longer explicitly asking the programmer to say, I'm moving data from one memory space to the other, we're actually paving the road to developments like that, because people can then no longer complain and say, oh, now all my work suddenly needs to be changed again because I no longer need to explicitly move my data between the two different memory spaces. So that, yeah, is one of the developments in the direction where eventually we will have different types of processors all sharing the same memory pool. Yes? Right. Yeah. So at the moment, it happens that if you touch data from the GPU, right? So you have malloc managed malloced something on the CPU side. You've touched the data on the CPU side. The data sits on the CPU. Now, if you launch a kernel and it touches the same data, this page is being moved onto the GPU, and it stays there. So if you're not trying to access data that is being used by the GPU at that point from the CPU, you will get a page fault. So it's up to the infrastructure, the programmer, to make sure that you're not violating these constraints. The worst case that could happen otherwise would be that, yeah, you're having, while the kernel executes, you're having the data being flushed back and forth. But so there is only a single copy, a single instance of your data. It's either sitting on the GPU or it's sitting on the CPU. And yes, you have synchronization primitives, CUDA device synchronize for making sure that you're actually, the CPU and the GPU are both in a defined state, and you know whether, yeah, who is at what point, and whether you can access now data safely from the GPU side, because you're guaranteed that from the CPU side, because you're guaranteed that the GPU has completed its work. So yeah, there's not really atomics that go across the wire, but there's synchronization primitives, and it's sent up to the programmer to make sure that the atomicity of the access is guaranteed. Oh, okay, yeah. Yeah, again, you have a fixed granularity of your memory chunks that are being touched. I mean, those are the memory the page tables, and so yeah, it's not the whole mechanism is not based on your variables, but it's based on these pages. So if you have a huge array, it will only be these chunks that you're currently touching that will be moved over to the GPU. Yes?
As I understand it, this works for the heap right?
It should also work there. It should it definitely on Maxwell timescales. I mean, at that point we have exactly the same. We know exactly based on the pointer where it's being located at any given time. I am. Yeah, you would get a page fault at that point. You probably end up in a humongous issue there, unless you're blocking the CPU. I mean, you can still lock your CPU at that point and just hope that you have another thread that can execute on the CPU side while your GPU is processing. So there's conceivable situations where it even might make sense. I currently don't know if it's worth a try. Actually, I think I should know, and I'm fairly positive it should also work. But I'm very positive on the Maxwell timescale. Given that you're not allocating your stack with CUDA malloc managed, there's on the other hand, a fairly sizable chance that it's not going to work. Give it a try. Okay, so that's for the unified memory. Again, CUDA 6 is not going to be ultimate performance. It's really more for trying to figure out what the use cases are. A similar method has been followed. A similar path has been followed with CUDA 5 and dynamic parallelism. It was another one of those technologies that got introduced first. People could experiment with it and gain some experience. And then with CUDA 5.5, there was more optimizations, and with CUDA 6, there's even more optimizations on the dynamic parallelism side. But yeah, we simply cannot deliver the ultimate solution out of nowhere. We first want to figure out how are people using it, and what are the necessary optimizations that how do we need to prioritize the different optimizations. Okay, so that's on the library side. One thing is that even though systems like 2D only have a single GPU per node, there's actually a broad range of devices out there, clusters that have more than one GPU within a single node. And so what the new library, the XT, the extended library interfaces allow for is that they automatically parallelize across multiple GPUs within the same node. So this is not across nodes. This is not PBLAS type of parallelism, but it's within the same node. Yes? Oh, sorry. sorry. I thought you were racing. Okay. Another benefit of this is that we're also seeing increasingly GPUs with a so-called Gemini configuration. So what you currently have in Kepler, in 30 or in Dane is a K20. We also had a K10 model that came out about a year ago, which is optimized for single precision performance. That device consisted on the same physical board, had 2 GPU chips. And right to the system, it presented itself as 2 independent GPUs. And that's something that might happen in future again. You can imagine if you're growing a chip, if it's a monolith, there is much more potential for failure, and it might become much more expensive than having 2 pieces and gluing them together. So from a production perspective, it might make sense to have multiple chips instead of just one. So yeah, there's a desire to at least give the user a mechanism of simply taking advantage of multiple GPUs within the same node. That's currently supported in cuFFT and BLAS 3. We also have now support for out-of-core matrix operations. So again, people complain about the 6 gigabytes of memory or the 12 gigabytes of memory that they have available, that this is insufficient for their particular problem. What these libraries do is they now do out-of-core operations that transparently swap in or stream these matrices to the GPU and back out again. And as an extension of this technology, we also have a drop-in interface for BLAS 3 calls that, that just transparently move the data to the GPU, perform the operation, and move it back. You're obviously getting optimal performance this way because you're possibly moving too much data between host and GPU. But you can do the math, and you will see that at matrix sizes of about 300 or 400 elements squared, for DGEM, it starts to pay off to move the data from the host to the GPU, process the data, compute the matrix product, and get the data back. That still can be faster than just computing the matrix product on the CPU itself. It's not going to be a huge speed up, but that's roughly where you break even. And any larger matrices than that will see a net benefit. So as you can see, it's another bit in this theme where we're trying to just make it easier for people to get started on GPUs. And yeah, that's just some performance numbers here. And here is for the out-of-core application, right, where you're seeing that you can actually get to very large matrices now that previously were limited at much smaller problem sizes. And the drop-in BLAS, I think I've covered all of that. For the GPU Direct RDMA, again, that's not really something that you need to see as a application developer, but fact is that it's now easier for middleware vendors to take advantage of the fact that we can move data straight from GPU memory to another device that sits on the same PCIe Express bus. In most cases, that means that you have a mechanism to quickly move data between GPU and the network interface. I've never used it. I've never written a transfer or a middleware layer application that takes data straight from the GPU and moves it to another device. So I cannot really give you any hands-on experience there. But it's definitely worthwhile to, if you have a situation like that, talk to us and we can find the people who can help you to take maximum use of it. Now on the developer tool side, I think that the coolest part is that the tools are now geared towards remote development. And so there is now the possibility to develop locally to have an IDE on your laptop, and your files, your GPU-enabled system is remote. And so under the hood, it will just transfer all the stuff via SSH or SCP. So that's, especially in situations like here, can be very beneficial, that you have the low latency and the responsiveness of a local development system, and yet still can take advantage of all the stuff that you have, all the compute power that you have here. And this is both for editing. I mean, Emacs users, for instance, had that for decades. So I think there's also a VI module for that, but here it's for just at the level of the entire IDE. And it's also at the level for debugging and profiling tools. Another thing is that, remember yesterday I mentioned this MultiProcess Server. So the fact that you can, or the technology that allows you to share the GPU efficiently between multiple MPI ranks. One of the downsides there was that we didn't have a good mechanism of profiling and debugging under those circumstances. Basically, the tools did not work with that. That has been fixed now, and so with CUDA 6, you can now debug and profile applications that run under MPS. Can be very beneficial because right, the problem otherwise is that you're scaling an application and you can only capture your profiles based on a single thread or a single MPI rank per node, and then you have to somehow extrapolate and figure out what could be the performance when you're now sharing this node with, or this GPU with multiple MPI ranks. So that can be a huge benefit. The profiler can also give you more information about kind of the pieces of code that use the most time. Now at the, this is the assembly, that's the so-called SAS code of that particular line of code. So it can present you the SAS and the source in the same, kind of in the same display, allows you to quicker see what's happening, how, yeah, is there anything that doesn't look right, anything that smells bad? Right, that's the whole point about looking at SAS code. Nobody expects you to really go through the individual instructions here and figure out what really happens on an instruction by instruction level. It's more, when you're seeing a lot of convert instructions there that convert between 32 and 64-bit floats, might not be optimal. Or you see that there's no LDG instruction there, and even though you were hoping through your use of const restrict that it would use the LDG instruction, well, maybe not. Something else went wrong. So, or if you're a total nerd, you might want to optimize at that level, but that's, and then in previous generations of the profiler, you just got kind of a combined view of the resource utilization. I think I mentioned that at least to some of you yesterday that, right, within each one of the processors, within each one of the streaming multiprocessors, we have a whole range of different pipelines that execute our instructions. And right, we have a pipeline for 32-bit, for 64-bit float operations. On the 32-bit, we actually have different parts, like one pipe that's responsible for special instructions, for special functions, some for just regular multiply and adds. It used to be all mushed together. You could get to the data when you were really digging for it, but it wasn't nicely presented. And now with CUDA 6, you have a much nicer presentation. And so you see, for instance, in this diagram here, you see that, well, you probably know that you're not using any double precision numbers, but here you're seeing that your floating point operations are only responsible for whatever, 45% of the overall cost. So maybe you thought that you were dominated by floating point operations, but then you realize, oh, actually I'm dominated by integer instructions. And that can give you a lot of hints of where you might want to look for some places to tune your application. Again, the information is already here in CUDA 5.5, actually in CUDA 5. You have access to these counters. It's just the problem with the basic counters is that they require quite a bit of understanding of how the architecture really works in order to interpret them correctly. It's like things like, are we talking about memory accesses? Is it measured in segments, or is it measured in bytes, or is it measured in cache lines, or is it measured in whatnot? And I mean, there's people who know those answers, but it cannot be the responsibility of you to know all these bits and pieces. What you really care about is how much of my bandwidth am I using, and so you don't want the raw counters, but you want to have human understandable data, and that's now much nicer presented in the CUDA 6 profiler. All right, so if you want to register, it's at developer.nvidia.com. You can register as a registered developer, and then you get access to the early release, or to the release candidate of CUDA 6. So this was it on the CUDA 6 side. Now I'm trying to figure out if we should go for the streams or rather for the shared memory optimizations. And what else do we have in that presentation? I think, for now, I think we should postpone the additional optimizations. Shared memory optimization is one thing that, again, especially when you're reading older CUDA literature, there's a lot of talk about bank conflicts and so on. But it's probably considered a mid-level optimization. It's not really one of the core optimizations that you should focus on. Streams are kind of on the more important side. So let's jump to the streams, and then come back to the other optimizations later on. Oops. Right, so what streams allow you is it's a mechanism to get more concurrency between the host and the GPU. And we looked at that yesterday in one of the profiles. I mean, what you really want to do, you want to be able to use the CPU, you want to use the GPU, and you want to do any kind of transfers in between as nicely overlapped as possible. And that's exactly what streams are for. So we have the typical offload model where we have the CPU and the GPU. You move data from the CPU to the GPU. You compute. You get the result back. And you do this several times. So if you look at the timeline, what that means is, right, you're starting out on the CPU. You do a host-to-device transfer. You compute on the GPU. And you do a device-to-host for to transfer the result back. And then you continue doing this and do this more and more. So when you look at the utilization, for this whole duration between this 1 and 2, your GPU just doesn't do anything at all. But it's not only the GPU that's underutilized, it's also the CPU that's not doing anything here in between. Now, MPS is one mechanism that helps you fill those gaps, right? So you could, if you now had multiple CPU threads or CPU processes share the GPU, well, they could be processing something during that time. But maybe your application is just not suitable for this type of overlap with MPS. So what you really want to do is a way of starting out with the host-to-device transfer. Start with the CPU computation, do the host-to-device transfer, and now do the CPU computation for the next chunk, for the next part of your work. And then as soon as the data has arrived on the GPU, you want to start to do the transfer of the second piece of work, the second data set to the GPU, and so on and so forth. So you want to pipeline the whole process. And this can give you a tremendous benefit compared to the non-pipelined design. And so the question is, how can you write this? So any kind of operations that you're doing with the GPU happen in a stream. Okay, so whenever you write a hosted device, a mem copy, that happens in a stream. Whenever you launch a kernel, that happens in a stream. A stream is kind of a sequence of operations that involve the GPU that are processed in order. So any kind of operation that goes to the same stream will be completed in steps. However, the execution order of operations that sit in different streams is non-deterministic. That's just depending on what the resources, the availability of the resources is. And the way you're specifying a stream is by adding a fourth parameter in your kernel launch. We never talked about the third one. The third one is actually a way of dynamically sizing the amount of shared memory that you're allocating for a kernel. There are some use cases for this, but generally not tremendously necessary. But so, yeah, when you want to add a stream to a kernel, you need to specify the size of your dynamically allocated shared memory. You can just set it to 0. So a kernel launch involving streams is blocks, threads, 0, and then the number of the stream. Now, so far, we've never used a stream. The question is, what happens then? And so we have the so-called default stream or null stream. This is the one that is available without explicitly specifying. So when you're not talking about streams, when you're just writing your CUDA application, you're guaranteed that your transfer of data will be complete before a subsequent kernel will be launched. And if you now have, after this first kernel, a second kernel, you're guaranteed that the second kernel does not start until the first one has completed. So that's what the guarantees that you get with using the null stream. Now, the kernel launches, even when you're using the null stream, kernel launches are still asynchronous with respect to the CPU. Right? You're kind of like queuing up all these kernel launches into one stream. But you're guaranteed that the kernel 2 will not start before the kernel 1 has completed. Now, this is only when you're using a single stream. But if you're using multiple streams, then you're actually getting the situation where if the resources are available, there can be concurrency. So for instance, if you're doing a mem copy in one stream and the kernel compute in another stream, well, they're completely independent. The resources are available. So there's a high likelihood that those kernels will be, or those operations will be performed at the same time. And yeah, I mean, that's the question about having multiple kernels that execute on the same SM. You're still bound to the the restrictions that you have on the SM, that that there needs to be sufficient shared memory to have another thread block of a different kernel executing on the SM. Yeah, all the hardware limiters that we previously had for that limited our occupancy, those limits obviously still exist. Those are just different ways of looking at concurrency that you can achieve, right? You can have multiple transfers at the same time. So on a K20X, you have 2 copy engines. That means you can have one copy from host to device and one copy from device to host at the same time. So like that's over here shown. You have a device to host and a host to device. You can have a very high number of kernels that execute at the same time. It's actually a configurable parameter, but it's on the order of either between, from a hardware perspective, I think it's at 32 kernels that in theory could execute at the same time. So there's a lot of room for creativity. Yeah, and what you then see here is, again, just an example that by using the multiple streams and being able to overlap all the host-to-device transfers, you can actually achieve a very high, in this case, a very high flop rate compared to the original serial implementation that just had that wasn't pipelining so nicely. Now, what do you need to do, I mean, in order to use streams? I mentioned that you have to have the fourth parameter when launching the kernel that indicates your stream ID. Well, there's a few more API calls. There's a special type for a stream handle, CUDA stream T. You have to create the stream, and you have to destroy them. So there's just API calls for that, CUDA stream create, CUDA stream destroy. And there are some mechanisms also to fine-tune the mechanics of the creation of the streams. Again, it's not tremendously necessary to know all the details of that one. Yeah, these are now just different use cases of this configuration. So in the simplest case, without specifying a stream, we're going into the null stream or the default stream. So the CPU kicks off the work and it processes in this null stream. And then the CPU kicks it off. Because it's the kernel launch is asynchronous, the CPU will continue, and even while the GPU is working on the first kernel, you're continuing and you can kick off the next kernel. And so this one will be just executed one after the other. Now, when you're using both the default stream and a user-defined stream, so you have a stream one, you use CUDA create stream create, sorry, and then you're launching the kernel. This guy has not a stream specified, so it goes into the null stream, and then you use explicitly your user-defined stream. What happens is that the first launch goes into the null stream, and the second launch happens afterwards. Now, in theory, you probably introduced this stream because you wanted to have concurrent execution of kernel 1 and kernel 2. But it's the semantics of the null stream that it guarantees that any kind of work will happen only after a kernel launch in the null stream has completed. So the null stream is special from that perspective. So if you want to achieve true overlap between those guys, the way you have to do it is to have actually two streams. So you have to have an explicit stream both for the first kernel and the second kernel. And in this case, you're getting the overlap as you wanted to get them. So now this is probably one of the biggest pitfalls in using streams, is that for whatever reason, you forgot to explicitly use a stream in one kernel launch, in some library, some far away, and therefore, yeah, you're serializing, even though you were intending to have concurrent execution of the different parts of your code. Yeah. Well, so first off, this would not be occupancy. Keep in mind, occupancy is just for terminology reason. Occupancy is the defines of how many warps that you can have on a single SM with respect to the maximum number of warps. Most likely, what you're running into is just device utilization, so that you're not using all the available streaming multiprocessors, or that you're already using all the streaming multiprocessors with each one of the kernels. Right? So assume that you're launching 2 kernels, right? And the first kernel uses 100,000 threads. And the second kernel uses another 100,000 threads. Well, they're not going to execute concurrently. Right? So you're not guaranteed that that kernels that are in separate streams will execute at the same time. All you're doing is you're giving the runtime system more information about dependency of the work. You're saying, hey, look, I tell you, this one, in theory, could happen at the same time. I'm not assuming in my design of the application anything about the relative order of the operations that happen in stream A and the operations that happen in stream B. But if the work in stream A already completely utilizes my GPU, well, there's no point in starting stream B at that. So the way you want, if you want to make an experiment and actually see concurrent execution, make sure that you're using grids that are very small. Right? Use a grid that only has 5 thread blocks. At that point, with 5 thread blocks, you have 14. Right? In theory, you have 16 times 14 thread blocks that can execute.
At that point, each kernel takes longer. So if I'm fully utilizing the hardware, it doesn't matter.
Right.
One way or the other.
I mean, it's just another tool that can, if the situation calls for it, allows you to get more overlay, right? There's some algorithms that simply don't have more parallelism than 512-way, right? If you're, for instance, matrix multiplications, if you're doing small matrices, or the ones that I had, 5x5 matrices, well, you only have 25 elements. There's just not more parallelism in this. Maybe if you're creative, you can add a few more. You can add it, multiply it by a factor of 5, if you're really creative. Okay, so then you're at 125-way parallelism, but still, you need 30K way parallelism. So with 5x5 matrices, there is a certain chance that if you have one thread block that only processes one of these products, that you can compute concurrently if they are launched in separate streams. So yeah, that's actually a very fundamental point. It's by putting stuff into 2 streams, you're not saying anything about the scheduling, the relative scheduling of those kernels. You leave that all to the runtime, to the GPU scheduler or the driver. There is no guarantees that they will execute concurrently. It's similar to the const restrict thing, right? With the const restrict pointer, you're also not guaranteed that your compiler will introduce the special load instruction. But you're giving the compiler all the information that it needs, that it can make the decision that it wants to do that. The same here. You're just helping the runtime to utilize the device if the resources would be available. You're telling it already, hey, there is independent work. By the way that I've structured my kernel launches, I'm telling you this is an independent kernel launch. If you have available resources, go for it and use it. And actually, so even in case where you have, one thing that you're probably observing often is you're probably not getting a nice overlap like that where you have really the full kernel running at the same time for most of the duration. But what you're seeing is that like the tail of the first kernel, when the when the number of thread blocks that you're processing is not a nice multiple of the number of thread blocks that could run at any given time, well, then you're ending up in a situation where at the end, you have just 3 or 4 thread blocks that still need to be processed. And then you will see that at that point, the next kernel will start, especially when it has been launched in a separate stream. Tail effects, that's also one of the benefits. So yeah, when you look at the real profile, you will often see then, when you're using streams, that you have execution of one kernel, and then there's some overlap phase where then the next kernel starts. Now, in addition, probably the more important case, rather than having concurrent kernel execution, is to have asynchronous memory transfers with respect to the kernel execution. And so for that, you shouldn't use just the regular CUDA mem copies, but you want to use the CUDA mem copy async. Yes? No. I mean, you're responsible for memory management there. So when you're when you're asking for more space there, well, at one point you just run out of memory, and then your CUDA malloc will fail. Yes, I mean all these calls, all the CUDA API calls, they return you error messages. No, but at time of mem copying, at that point, your arrays already have to be allocated on both the CPU and the GPU side, right? So if you, and yes, you can definitely copy more data than you allocated, but then you're ending up in an unspecified launch failure. I mean, in the equivalent of a seg fault. So yeah, the time when you will discover that you're running out of memory is at the time when you're allocating. So it's at CUDA malloc time. And the CUDA malloc calls, they're all synchronous. Right, so there's nothing like a CUDA malloc async. And therefore, yeah, at that point you will know if you have sufficient space or not. So if you want to have overlap between kernel execution and memcopy, you need to use CUDA memcopy async. There is one caveat that on the host side, there is actually two different types of memory. In the simplest form, you have pageable memory. So those are memory pages, and I think I have another slide on that. Yes. So usually when you just do a regular malloc, these are memory pages that the operating system at any given point could say, oh, I'm moving them to disk, or I'm moving them relative to the physical addresses. With pageable memory, you cannot actually get the, if you're copying out of pageable memory, you cannot get overlap between kernel execution and data transfers. The reason is pretty simple, is that right, when you're doing these transfers, you want to do that from a physical piece of memory, from actual memory on the host side to actual memory on the GPU side, right? So the underlying hardware needs to touch real memory at that point. And so if it was pageable memory, well, it could be that whatever seemed to be the correct address, the physical address of these of this data, while you're transferring the data, is no longer a valid address. It does not contain that page anymore. So what you need to do is you tell the operating system on the host side that, hey, this is a chunk of memory that has to be real physical memory, so-called page-locked memory, or pinned memory. And you can do that. You can do that by calling a CUDA malloc host. There's actually another form. Some things are just historically given that initially it was somewhat of a different definition or a different name that turned out to be a fairly poor choice. But there's also CUDA host alloc and CUDA free host or host. I'm not sure if there's a host free. But in any case, those are the calls that allow you to allocate pinned memory. Now, in those cases, keep in mind that you're actually touching real memory on your CPU side, and you're setting this memory aside. No other process can ever touch that. And so, yeah, you can quickly fill up the available memory on your system. So it's a resource that should be used scarcely. I mean, when you're doing, so just one thing to keep in mind when you're doing a transfer, a CUDA mem copy from pageable memory, what actually happens under the hood is that your chunk that you're trying to transfer from the host to the GPU will be chopped up in small parts, will be copied on the CPU side from pageable memory into page-locked memory. Those segments are just managed by the CUDA driver. So they're copied into a chunk of page-locked memory, are being transferred over to the GPU. And so that's why you're not getting the theoretical bandwidth that the PCIe Express bus could deliver, because you're copying this data even on the host side multiple times until it actually is being shipped across the wire. Yes? I would assume that you're getting a completely new page, yes. 1 byte, yeah. I would assume that you're actually ending up in as many pages as you have bytes. But the point here is that if you're in the situation where you're actually transferring individual bytes across the wire, across the PCIe Express bus, then you're probably suffering from fairly low transfer performance anyway. Right? Because it's fairly expensive to just kick off the bus to transfer data. And so in order to optimize the data transfers, you probably want to have sizable chunks. And I think I have a number somewhere, 4K or larger, that you want to transfer at any given time. So yes, I'm fairly positive that you're actually ending up with having multiple pages for each one of the calls to CUDA malloc. CUDA malloc host, sorry. So yeah, you can use this special allocator. You can also take pageable memory and just tell the operating system, you're just telling the operating system that, oh, by the way, from now on, don't view this memory as pageable anymore. Use it as true physical memory. Yes?
Now, since you say I will achieve a low bandwidth with pageable memory, copying pageable memory, should I do this also if I do not have streams at all?
You can. I mean, the only flip side is that you're limiting the amount of memory that's available to the rest of your system. But if you're fine with that, then yes, there is no downside to using CUDA malloc host. There is actually one somewhat downside, is that given that you're involving the operating system, it's actually a fairly expensive operation to do a malloc host. But then again, if you're gearing your application for performance, you're probably separating your memory allocation into whatever, an initialization phase anyway. And at that point, this extra cost becomes marginal.
But I can't use the memory that has been allocated on the host side with CUDA malloc host, and use it as normal.
Yeah, it's exactly. It's your conventional memory. It has no other side effects. The only thing is that it's true physical memory. The operating has no chance of moving it out. So once you've used up all your 16 gigs or whatever you have, you're just stuck. I mean, yes? Yeah. I mean, under the hood, it's exactly that what it does. It's just that, right? We try to be portable between Windows and the different forms of Linuxes, and therefore, we have another wrapper around it. But I mean, yeah, you can also just do a regular malloc and use CUDA host register afterwards. I mean, that would be the same thing. And CUDA host register just does exactly the same thing as you would in your preferred operating system. The mechanism you would use to page lock or to lock some of the pages that you've allocated. Yeah, so that's just an example, right, of using CUDA malloc host. So similar to it's the same control flow as you would have with the regular malloc. You're now just doing a malloc host and a free of that one, and this way you now have a pinned memory on the host side, and we can use the stream, and we actually get the benefit of this stream as we would be hoping for. And as I mentioned before, right, instead of using CUDA, damn it, CUDA malloc host, not host alloc, CUDA malloc host, you can also just use a regular malloc and then do a host register. So these are the 3 examples, similar to the ones that we had before with the concurrent kernel execution. Here now just with the data transfers. Right? If you're not using any streams, you're guaranteed that the operation, any operation in the null stream is nicely is synchronized. I mean, it happens in lockstep. So your mem copy will be completed, and once the mem copy is completed, your kernel will start executing. If you're using a CUDA mem copy async and a stream for both, well, if they're in the same stream, with the async, you're actually telling on the CPU side that you can make progress while the transfer happens. Right? So in the first case, with the data transfer, it was actually waiting until the data transfer has completed and only then continue to work. With the stream, your CPU is free to do additional work, for instance, launch a new kernel. But given that both the mem copy and the kernel execution are in the same stream, they happen one after the other. And then if you're using 2 different streams, you will also get an asynchronicity between the data transfer and the kernel execution. So you can get very creative in the concurrency of GPU execution, CPU execution, and all the transfers in between. I'm not going into the synchronization. So there's mechanisms for whenever you have highly asynchronous execution, there has to be some form of querying how much progress has one of them made, and forms of synchronizing to make sure that you're in a well-defined state again. And so for that, we have this mechanism called events, which are basically just markers in each one of the streams that you can query, and you can figure out, have I reached this point in my execution? So you can synchronize on events, you can wait for events in another stream, so you can do a lot of, again, synchronization between the asynchronous execution. And for sake of not frying your brains this morning, I will just hop over this. Again, once you sit down and you figure out what your situation really is, it's not complicated. Just imagine, an event is basically just a minimal kernel that sits in a stream that allows you to query the state, whether this kernel has been reached or not, well, whether this event has been reached or not. We don't have a mechanism of querying completion of a kernel, but we have a mechanism of querying an event if that has occurred. And that allows us to figure out if a stream has reached a certain point. Yes? No, the kernel events are currently not supported on the kernel side. Right? So the way you have to do it is that the CPU launches the kernel and then inserts an event into that stream. Actually, do I have to? So let's look at this case down here. So the CPU starts out launching in one stream this hosted device, the yellow one. And then it puts an event into stream 1. So this is just this minimal kernel, the red one back there. This all happens asynchronous. The CPU continues processing. It now puts another data transfer into another stream and puts another event into its stream. But now it says, in this particular case, it puts this event, and it says CUDA stream wait event. You're linking progress in stream 2 to reaching an event in stream 1. Okay, so even if the execution in stream 2 doesn't take the full time, with this stream wait event, you can tell stream, in this case stream 2, that it has to wait for the event in stream 1 to occur. So that's a mechanism of synchronizing the two independent executions in stream 1 and stream 2. There's a way of an event query. And so at that point, you can asynchronously see if this event has already been reached or not. Yeah.
So basically, you can create a kind of flowchart of execution of the different streams, no?
Exactly.
But this flowchart is then moved to the GPU and then executed over there. So there's a lot of intelligence moving to the GPU, or the synchronization is performed by the CPU.
Well, as you can see here, this particular synchronization here, at that point, the CPU is not involved. Yeah, so you have the wait event. This one is just on the, yeah, this happens all on the GPU side. Yeah. So yeah, there is this. Yeah. Complex dependencies, yes. Yeah, but you still have to put this stuff into the streams from the CPU side. So you're still doing this, right? Inserting these events still happens on the CPU side. So you basically, right, that's all the stuff that happens here. Right, you're still building this flowchart on the CPU. Right. But then once it's on its, yeah. Yeah, I mean, we have people in the room who have exactly this problem, that they need to stream through all this data that comes in from some detector or whatnot, and they don't want to do the massaging on the CPU side. Ideally, it just goes from the network straight on the GPU, and the CPU just stays out of there. And yes, I mean, what that allows us is eventually to get rid of this guy, or to make it very, very thin, very low performing. Now, there's with asynchronicity, there's always a big chance for mess up. Right, I mentioned the potential danger that you by accident have a kernel launch in there that uses the default stream, and it will mess up your entire asynchronicity that you've set up so nicely. Or that you're not using the right transfers, or not coming from pinned memory. That's all stuff that the profiler will tell you. So when you look at the NVVP, it will immediately tell you that this is not coming from pinned memory. Also, when you debug, it's sometimes better or easier if you avoid the asynchronicity. But rather than modifying the code, you can just throw this this environment variable, CUDA launch blocking. You can set that one, and you will be guaranteed that any kind of operations now happen in sequence. Right? Again, with having even two kernel launches in two separate streams, you're not guaranteed that they will be executed at the same time. You're never getting any guarantees that stuff happens concurrently. You just give it the option to execute concurrently. And that's why a code always still has to be working correctly, even if you're serializing every single data transfer, every single kernel launch. And so that's why it's even possible to have this mechanism that serializes all the individual steps. What other hazards do we have? Those are more of the lower level ones. It's like, yes, you could overload. Yeah, you could have too many outstanding kernel invocations or operations in different streams, but I would say that those are not really issues that you need to worry about. Okay. Where are we time-wise? We're getting close to lunchtime. Yeah, I think I mentioned this one yesterday, that right with the different streams, I mean, you depend on, yes, sorry. Yeah. Modulo bug, but yes, it should all be thread safe. Yeah, actually, so in previous generations of CUDA, you actually had to use multiple host threads if you wanted to, let's see, you had to have a host thread associated with each one of the streams, I think. That was at the very early times. But now it's, yeah, this is all gone. I mean, now you actually don't need any kind of, you can use, as I said, in theory, everything is thread safe. I can actually say everything is thread safe, but the, yeah, so you can use multiple threads, but you don't have to. Even if you're using multiple GPUs, you can talk to all of the multiple GPUs from the same CPU thread. Again, that was another limitation, that previously you had to use multiple threads if you wanted to touch them, if you wanted to touch multiple GPUs. So that has been simplified quite a bit as well. Now, just one thing that, yeah, yesterday I mentioned that on the Fermi side, it used to be the fact that the way the kernels were executed from the different streams could easily lead to the situation where, even though work was potentially concurrent, the hardware scheduler couldn't see that. And with, so you had to be fairly careful in how you would put stuff, how you would launch the kernels in the individual streams in order to guarantee that you would indeed get concurrent execution of these, of the kernels. With Kepler, that's now much more improved, where you're giving we give the hardware much more freedom of selecting the next available kernel that could be launched, and therefore, yeah, you will have much less troubles to see nice overlap of execution on the GPU. But again, it still depends on the availability of resources. I mean, if there is no more SMs available to hold this kernel and execute it, yeah, it will be serialized. And so, just to give you a feeling for the visual profiler, right? How does it look like? So up here you have the timeline, and again, using the visual profiler for this kind of asynchronicity of figuring out what really happens and whether you see the asynchronicity that you're expecting is a must. And so up here you see two host threads that are executing something. Here in the next group, that's usually the brown bars, you see the memcop is, it would be host to device, device to the device to device, and device to host. And then you're seeing in this block, you're actually seeing the overlap. If in this, what is labeled, you can't see it before, but it's labeled as compute. If on the compute side, you're just having one line and everything happens after each other, there's no overlap at all. But here we have 3 lines of kernels or of transfers that happen at the same time. And so you're seeing that there's good overlap. And then you have, in all the different streams that are used in this application, you see the activity. And yeah, depending on how many GPUs you have, we have here a first and a second GPU in this system. So you will see that for both GPUs. So you get a lot of information about the concurrent execution by just staring at these timelines. Okay. Rule of thumb, again, just first make sure that you have syntactic correctness, introduce, or semantic correctness, then introduce the streams. And at one point, just, yes, synchronize only when it's really necessary. And let those streams be scheduled by the hardware as independently as possible. And yeah, use the profiler to make sure that you're actually getting the overlap that you're hoping for. Okay, this is it, yes.
The command line profiler, I think we talked about what the name was.
Mm-hmm.
That doesn't produce any fancy ASCII.
Any fancy ASCII art of this one? No, unfortunately not. But I mean, it's hard to extract from the NVProf directly. However, when you do NVProf -O for the output file and then my profile, then you can import my profile into NVVP and then look at it from there. And then you see all this, then you see exactly this. So that's how I usually work here on one of the systems at CSCS. I mean, I have a fairly slow connection to here. And so I'm running NVProf on one of the systems, and then I'm taking the output, transferring it back to my workstation. And then you also have the nice responsiveness of the interactive tool. CUDA 6 does that for you under the hood. But yeah, that's CUDA 6 is not yet there. Yes, I mean, so, well, then that depends on what you're looking for, right? In one case, you're just running NVProf with an output. This gives you only the information about the timeline. But for looking into concurrency issues or just getting the basic information of what is the occupancy of this kernel, how many threads am I actually using, for that it's enough. And especially at the beginning when you're looking into an application, that's the type of questions that you usually have. But then, yes, you're totally right. If you want to drill down and get all the metric information, either you do NVProf -- analyze or analysis metrics, and you transfer it, and then you get all this information, or alternatively, you use VNC as a mechanism of just getting better responsiveness on your laptop or on your local system. So yeah, that's. Is VNC actually available on 30 as well? Okay. Yeah. I think I know from Castor. On Castor we had it, but. Okay. Yeah. But I mean, the thing is that the format of the profiles doesn't really depend on the architecture you're running on. All that matters is that you have the right version. I mean, you need to have whatever CUDA 5.5 NVVP. But once you have that on your local workstation, then you can read the profiles that were generated with NVProf on the 5.5. Okay, so that's it for the streams. I think we could go for some energy. But otherwise, I would then say in the afternoon, let's go for. Well, let's figure out during the lunch break whether we want to go more into shared memory optimizations or more on the jump straight back to the exercises and probably do some interactive analysis with NVVP. I mean, we could also do that. Yes? In theory, no. I mean, you have your stream ID is an integer, and that can be as large as you want. But in practice, yes, there is a limit of